So today we're going to look at all the mathematical requirements for topic 6, rates of reaction, which is on paper 2 of chemistry. We will look at what's needed for a foundation level and the additional requirements for the higher level. Now, as always with rates of reaction, we need a set of results. So the context which we are using here is a fairly common one. We're looking at the reaction between marble chips and hydrochloric acid. In this experiment, the lossy mass was being measured at regular time intervals. And these are our results. As you can see, the lossy mass was worked out for every 20 seconds, all the way up to 2 minutes, 120 seconds. Now, obviously with rates of reaction, the first thing you have to do is to draw a graph. So here we go. So the first thing we have to do is to determine our scales and then suitable axes. So in this, the time, which is what we controlled, is the x-axis. It's the independent variable. And the lossing mass, is which we measure as a result, is the dependent variable, and that becomes the y-axis. So our time goes from 0 to 120 seconds. Our mass, lossy mass, goes from 0 to 4.0. So let's get a suitable scale. So looking at a suitable scale here, every 10 seconds is one large square, and we go all the way up to 120 seconds. Now I'll do this, I'll add on now the y-axis for. Now I've got the suitable scale, the next thing is the accuracy of the plotting, and they're very precise about this. They allow you plus and minus half the square, so you need to be very precise. So at time 0, volume is, lossy mass is 0. At 20 seconds it is 1.6. Now I'll plot the rest and then we'll look at it in a minute. Now there we've plotted all the points. The next thing to do is to look at our line of best fit. And to do that, we need to look along the graph to make sure all the points lie on it. Now obviously this point looks anomalous, so when we are drawing the line of best fit, we do not include that in drawing our line of best fit. So let me draw the line of best fit up. And here is our graph with the line of best fit, noticing I've ignored the anomalous result. Now, very first thing they ask you is about the shape of the graph. So you can see we come up fairly steeply in this first 20 seconds. This is because the rate of reaction is fastest there, because there are most molecules of the two reactants. As the time goes on, the reactants start to get used up, so we get more and less successful collisions, and eventually when we get to this point where it is level, the reaction is stopped. So various things that you will be asked is like 1, when does the reaction finish? So the reaction finishes when it first starts to level off. So this is where it starts to level off. So ends at 100 seconds. Other things they will ask you are things like, how long does it take to lose a mass of 2.4 grams? So if you come across some 2.4 till you hit the graph and draw your lines on like this, is dotted lines, and then come down. at 90 degrees to the point. So 2.4 gram lossy mass equals, and that's going to take 36 seconds. Another thing will be, how long does it take to collect what lossy mass occurs after 55 seconds. So lossy mass after 55 seconds. Now to do that, we find 55. Again, we come up with a dotted line till it hits the graph. Come across from there. And the lossy mass after 55 seconds is 3.15 grams. Now, a third thing maybe is the lossy mass between, I'm going to say 20 and 40 seconds. So to do that, let's get our lossy mass at 40 seconds. So again with that, we come up for 40 seconds. And we can see that's going to be 2.6 grams. And lossy mass 20 seconds. So come up to hit the graph at 20 seconds. And that's 1.6 grams. So if we take 1.6 from 2.6, that will give us 1.0 grams. So those are standard things there. The next part are to do with rates of reaction. So there are three things that we need here. Is what's called the average rate. And the most important thing about rate is having the correct units. So if we look at it this way, that over the course of the reaction, we lost 4.0 grams. So the average rate would be loss in mass over time taken. So 4.0 divided by 100, and that will be 0.04 grams per second. So that's the average rate of the course of reaction. If we wanted, say, the rate over the first 30 seconds, so rate over 30 seconds, what we'll need to get is the loss in mass. So we will need to make our construction as per normal. And then come across to read it off. So the loss in mass is 2.1 grams, and over 30 seconds, which will come out as 0.07 grams per second. As you can see, that's a faster rate than the average, which you'd expect because the reaction goes much faster in the first 30 seconds. The next part is to find the rate at any particular time. Now, this is only on the higher paper, it's not on the foundation. And the reason is to do that, we've got to draw a tangent, and when we draw the tangent, we then have to work out the gradient of the tangent. So, to draw the tangent, we need a line which hits the graph at 50 seconds and only touches the curve once. So there we go. Now I've deliberately chosen here now, so it goes right over to cut the y-axis. So I can read off there. My time is 0 and I've drawn it to 80. So what we have to do now is complete the triangle. So completing the triangle will be like so. Come across from here. And then come up. So rate at 50 seconds will equal the change in mass. So here we are at 1.4, so this is 1.3. Here we are up here at 3.95. So the lossy mass is 2.65, and the time taken is from here to here, which is 80 seconds. And that will work out as 0.033 grams per second. So this is the reason why it's only on higher, because of the construction and the mass requirement of this. So remember, if they want the rate at a particular time, then you draw a tangent. Otherwise, it's just straightforward division. So the tangent, you draw your straight line so it touches the graph at that time. So I've made my tangent hit the graph exactly at 50 seconds. It doesn't cross it at any other time, and that's the important point there.